where we extract the essential logic from complex sources and basically hand you the precise knowledge you need to be well informed.
And today, we are getting into something really fundamental.
We really are. We're talking about the chemistry that creates the salt on your table, the
Hmm.
minerals in mountains, even the signals that, fire in your brain. We're talking about ionic bonding.
Mhm.
Now, our sources for this deep dive, they're structured almost like an exam survival kit, which is actually perfect for our mission here.
Yeah, it helps cut through the noise.
Exactly. We're not wading through every single footnote. We are going straight for the core logic, the mechanism, the right words to use, and the why behind it all.
And if you get this, you really get the concept.
Totally. So if we had to boil this entire, this whole deep dive down into just one sentence, what's the one thing you need to take away?
It's this. And it's the beginning, middle, and end of the story.
Yeah.
Ionic bonding happens because oppositely charged ions attract each other. And those ions get created when electrons are definitively transferred from a metal atom to a nonmetal atom. That's it. That's the whole game right there.
Okay, let's unpack that because that word transfer, that feels like the first major hurdle. It's where people trip up right at the start.
It is the number one mistake. Our sources flag this as the biggest danger zone.
So what's the examiner's checklist? What are the absolute must-haves for understanding this?
There are three non-negotiable points of logic.
Yeah.
First, and this is the big one, electrons are transferred. It's clean handoff.
It's not shared.
Absolutely not shared. Second, this transfer creates ions. The atoms are fundamentally changed. They're not neutral anymore.
Right.
And third, the bond itself is the electrostatic attraction between those new oppositely charged ions.
Yeah.
If you miss the transfer part, the whole thing just falls apart.
It sounds simple when you lay it out like that, but this is exactly where the trap is. The sources say if you use one wrong word, you've changed the subject entirely.
Precisely. If you're talking about ionic bonding and the phrase electrons are shared comes out of your mouth, you've just described covalent bonding.
And you get 0 marks.
0 marks. It's a completely different mechanism. So we have to treat the word transfer as, non-negotiable. It's the key.
Okay, let's make it concrete then. Let's use the most famous example there is. Sodium chloride, table salt.
Perfect. You've got sodium, which is a metal, and chlorine, a nonmetal.
So what's the logic here? How should we frame it in our heads?
Okay, think of it less like a partnership and more like a quick, decisive transaction. Sodium has this one extra electron in its outer shell that it's frankly desperate to get rid of to be stable.
And chlorine.
Chlorine is on the other side of the periodic table. It's just one electron short of a full shell, and it desperately wants to grab one.
So sodium just gives it away. It's not a negotiation.
Not at all. It's a clean break.
Yeah.
The metal gives the electron, the nonmetal takes it. Suddenly you have charges. A positive charge meets a negative charge. And what do opposites do?
They attract.
With a huge amount of force. And that powerful attraction is the bond.
Okay, that reframes it completely. It's not cooperation. It's a permanent exchange. And it's all driven by this need for stability.
Exactly.
So now that we've hammered home that it's a transfer, let's get into the why. Why are metals always the givers and nonmetals always the takers?
It all comes down to achieving a full, stable outer shell of electrons. Basically, they all want to look like the noble gases, which are super stable and unreactive.
Right. And the atom's own structure dictates the easiest way to get there. So let's start with sodium, the donor.
Sodium's in group 1. That means it has just one lonely electron in its outer shell. To get stable, it could try to gain 7 more electrons, which is, that's energetically impossible, or it can just lose that one. That is by far the path of least resistance.
And what happens to the atom's identity when it jettisons that negative charge?
Well, the number of positive protons in the nucleus doesn't change, but now it has one fewer negative electron. So the positive charge wins out.
It becomes a positive ion.
A positive ion, which we call a cation, specifically becomes the sodium ion, text 10 plus saying.
So wait, that's an interesting point. If it loses an entire electron shell, does that mean the ion is actually smaller than the original atom?
That's a fantastic question. Yes, it is. That outer electron is pretty far from the nucleus and loosely held. Once it's gone, the whole structure kind of contracts to the next shell down, which is now full and stable. So the text M plus I dollars is definitely smaller than the neutral sodium atom.
Okay, so then the nonmetal chlorine must be the complete opposite story.
Exactly. Chlorine is in group 7. It has 7 electrons in its outer shell. It is so close to being full.
So for chlorine, losing all 7 is just, it's not going to happen.
It's nonsensical. But gaining just one, that's the most logical, easiest thing for it to do to become stable.
And when it gains that extra negative electron,
The total negative charge now outweighs the positive charge from the protons. So it becomes a negative ion. We call that an anion.
so the chlorine atom becomes the chloride ion.
And there you have it. You've transformed two neutral atoms into a positive anication and a negative anion. The stage is officially set for attraction.
Which brings us perfectly to the bond itself and the structure. We have our two charged particles, you put them together, and what happens?
They attract each other with an immense force. And here we need to be really precise with the language. That attraction is the ionic bond. Formally, we call it the electrostatic attraction between the oppositely charged ions.
Electrostatic attraction, that sounds powerful. It's one of those key phrases the sources kept highlighting.
It really is. I mean, think of it like two perfectly shaped, super strong magnets. Once they snap together, it takes a huge amount of energy to pull them apart again. It is not a weak link.
And that powerful attraction is what dictates the whole structure of the final compound. It's not just one sodium ion pairing up with one chloride ion.
No, not at all. When these things solidify, they form these vast, highly organized three-dimensional structures. We call it a giant ionic lattice.
A lattice, so like a crystal structure.
Exactly. Picture a perfect repeating 3D checkerboard of charges. Every positive sodium ion is surrounded on all sides by negative chloride ions, and every negative chloride ion is surrounded by positive sodium ions.
So it maximizes all the attractions and minimizes any repulsion.
That's the architecture. It's an incredibly stable, strong arrangement.
Okay, so let's just quickly review the must-use language here. We have to say ions, transfer of electrons, electrostatic attraction, and giant ionic lattice.
Yes. And just as important is what to avoid. Don't say atoms attract, they're ions. Don't say sharing. And try to avoid vague stuff like one thing affects the other. Precision is everything here.
All right, we've nailed the mechanism, the players, the structure. Now for the payoff. Why should you care about this rigid lattice? I mean, what does it explain in the real world?
This is where it gets really interesting because it explains the properties. This is the chemistry on your stovetop. For example, ionic compounds like salt have incredibly high melting and boiling points.
Okay, and for a test question, the why is always the important part. How do we connect that strong bond to the high melting point?
It's a classic two-part answer. First, you state the cause. Inside that giant ionic lattice, the ions are held together by very strong electrostatic forces of attraction.
Part one.
Part two is the effect. Because those forces are so strong, you need a large amount of energy to overcome them and break the lattice apart.
So you need a ton of heat, a lot of thermal brute force just to get those little magnets to let go of each other.
It's a direct consequence. I mean, if the bond were weak, you could melt it in your hand. But because this attraction is so fierce, you need temperatures over 800 degrees Celsius for something like table salt. Your oven doesn't even get that hot.
So that's why salt won't melt in a pan. Okay, this has been a super focused deep dive. Let's run through the essential takeaways one last time. What's the self-check?
All right, 4 quick steps. First, metal loses electrons, becomes a positive ion, a cation.
Got it.
Second, non-metal gains electrons, becomes a negative ion, an anion. Third, the ionic bond is the electrostatic attraction between those oppositely charged ions.
And finally,
That massive attraction creates a giant ionic lattice, which explains why these compounds have such high melting points.
perfect. And just to leave you with a final thought, something that builds on this idea of bond strength that we've been talking about.
Okay.
We've established that the strength of the bond dictates the melting point, and the main thing determining that strength is the size of the charges on the ions.
Right. We use sodium and chloride, which are +1 in Maverin. A pretty simple case.
But what happens when the charges are bigger? Think about a compound like magnesium oxide. Magnesium is in group 2, so it forms a +2 ion.
And oxygen is in group 6, so it forms a nitric ion.
So now the charges involved have doubled. You've gone from +1 in Mad1 to +2 in Natica2. The force of attraction between those ions isn't just double. It's much, much stronger.
Oh, massively stronger. The forces holding that lattice together would be way greater than in table salt.
So here's the question for you to think about. If that attraction is so much stronger in magnesium oxide, what does that do to the melting point? We know salt melts around 800 Celsius. Based purely on the logic of electrostatic attraction, what kind of melting point would you predict for a compound with +2 and -2 ions?
That's a great question.
It really gets you thinking about how the fundamental nature of these ions dictates the real-world behavior of the stuff all around us.
It's a great place to leave it.
A great question to keep the deep dive going. Thanks for tuning in. We'll see you next time.